Today we hope to I hope to complete the matrix chain multiplication problem that we started off in the last lecture. And time permitting, we will look at one more and probably the last example of dynamic programming, which is also covered in the book quite extensively, which is the subject of optimal binary search trees. Okay. And I think both of these are reasonably interesting problems. As you might have guessed by now, I really like dynamic programming. And so I'm spending a lot more time on this. It's got some really cool features. So let's see how we can remind ourselves about the matrix chain multiplication problem. So just a quick reminder, what we started talking about in the last lecture is that the matrix chain multiplication problem basically says, can we optimize a series of matrix multiplications? Okay. So we have matrices of different sizes, different dimensions, and these need to be multiplied. So A1 times A2 through all the way through AN, n matrices, and we want to minimize the number of scalar multiplications, right? And we spoke about this, that there are some additions as well, but we don't want to focus on additions because multiplications take generally longer in computer inside the processor as compared to multiplications. So we want to minimize the number of scalar multiplications. And we reminded ourselves as to what exactly is a matrix multiplication. And we said, well, basically, if you have these two matrices, each one of them being different sizes, but obviously the number of columns in the A1 matrix has to be equal to the number of rows in the A2 matrix for a valid matrix multiplication problem. And then the final matrix, which is A1, A2, has the dimension P0 times P2. Okay, so P1 doesn't get into the equation in the final matrix. The number of scalar multiplications required, and we went through this in the last lecture, was P0, P1, P2, right? Because that basically corresponds to P0 times P2 is the number of elements in the final matrix, and each one of these requires a total of P2 multiplications, okay? P1 multiplications. That's why you have P0 times P2 multiplied yet by P1 to be able to calculate the total number of scalar multiplications. So I think that's almost where we stopped. We did one more slide, and basically we said, let's define the sequence of dimensions. The sequence of dimensions is simply the set of sizes of the first row, the second row, and all the way up till the final row, including the final column size. Okay, so you have P0, P1, all the way through Pn. You don't need to record the numbers which appear twice, because clearly the number of rows and the number of columns is going to be common in the matrices. So we can reduce this particular set of dimensions, and we can drop the extra numbers over here, and we can simply represent it as P0, P1, P2, and P3. Okay, so that's the sequence of dimensions. So essentially, when you have the matrix chain multiplication problem, you will be given this sequence of dimensions, which is representing the sizes of the matrices and the value of n. Okay, we don't necessarily need to know the actual values inside the individual matrices, because that is not completely relevant. Okay, and we essentially need to find out what is the best sequence of, what is the best way of multiplying this set of matrices. Now, you might think that there seems to be only one way of multiplying them, but clearly, if you think a little longer, you'll realize that obviously there are multiple ways of multiplying. Okay, so here's a simple example. So let's say that you have three matrices, n is equal to 3. The first one is 10 by 100, the second one is 100 by 5, and the third one is 5 by 50. Okay, and so the sequence of dimensions is P0 is 10, P1 is 100, P2 is 5, and P3 is 50. Okay. And so if you want to compute A1 times A2 times A3, then basically then it seems like there are two possible ways of putting the parentheses. Okay, so one way of doing the parenthesization is that we do A1, A2 initially, all right? It seems to be kind of logical, and then you multiply it by A3. However, you could also initially multiply A2 by A3 and then multiply it by A1. Right? So, quick question: would the resulting matrix in option, if you follow option 1 versus option 2, would that be the same? Yes. Yeah, they would be the same, and the reason is that it has the associative property, right? Because matrix multiplications are associative. However, of course, please note that if you change the order, then that would be the same. Okay, that's kind of obvious. However, the parentheses doesn't really affect the final resulting matrix. However, would the number of scalar multiplications be different if we followed A1, option 1 versus option 2? Would the number of scalar multiplications change? And how would you calculate the number of scalar multiplications now? Any thoughts? So we already know how to multiply two matrices, and we know the number of scalar multiplication for A1 to A2 is going to be P0, P1, and P2, right? But what about multiplying by A3 and then the second option? So can you figure out what the number of scalar multiplications would be in the two scenarios? Think about what we're doing over here. We're taking the sizes of the matrices, right? P0 times P1 times P2, right? That's what we did over here. We said that if you wanted to multiply A1 and A2, you basically said P0 times P1 times P2. Why is that? Because P0 is the size, the number of rows in the first matrix. P1 is the number of columns in the first matrix, which is equal to the number of rows in the second matrix. Okay. And P2 is the number of columns in the second matrix. So simply P0 times P1 times P2. That's the number of scalar multiplications. So now if you have these two scenarios, what would be the number of scalar multiplications? And how would you compute that? So basically, we know what A1 times A2 is, but that's just the first part. So it will now comprise of a series of additions, right? So you need to compute A1 times A2. We know what the scalar multiplications is that's P0, P1, P2. But now what about multiplying A1, A2 multiplied by A3? Yes, Yuvraj. Right? P0 times P2 times P3. Okay, so that should be correct, because you can see that once you've multiplied these two matrices, you get a matrix which is 10 by 5, right? 10 by 5. So the 100 sort of collapses. And so the resulting matrix becomes really small. It's just 10 by 5, even though you had 100 100 columns and rows in the middle, but because you did the initial multiplication, it became really small. And so when you finally multiplied by 5 by 50, then the second set of multiplications was P0, P2 times P3, which is 10 by 10 times 5 times 50. All right. And the first multiplication was 10 times 100 times 5. Okay. Now, if you think about the second way of doing it, okay, now, how would that be different? So we've got, so the sum of the first two will be the sum of this number plus the sum of this number, okay? This would be option 1. And can somebody tell me the option 2 figure? Let's put that over here. So now A2 times A3 is going to result, and what's the number of computations for A2 times A3? Somebody else. What's the number of computations for A2 times A3? Yes. P1, P2, P3, which is 100 by 5 by 50, right? Now you notice that there's 100 coming in there. So clearly now you're getting into much larger numbers. And then you're going to, so this is, and then what about A1 times the resulting matrix? How much is that going to cost us? So this is the first part, which is computing A2 times A3 and multiplying it by A1. What's the size of A1? That's 10 by 100. So what would be the number of computations to multiply a 10 by 100 matrix with a matrix which is A2 times A3. So first we need to figure out what's the size of A2 times A3. Yes. Ten times 100 times 50. Okay, so you can clearly see that multiplying A1 times A2 times A3, now this is resulting in much larger numbers. Okay, so here is the calculation. So the total number of multiplications. Now in general, you can think of it in the following manner, because this is going to come in handy as we go forward, is that if you're multiplying two matrices, then basically it's the cost of the first matrix, okay? The cost of the second matrix, however you're calculating it, times the cost of multiplying these two matrices together, okay? So in this case, multiplying this matrix by this matrix. So essentially the cost of A1 times A2 is coming out to be 5,000, right? A1 times A2 is 10 times 100 by 5, which is 5,000. This results in a 10 by 5 matrix. The cost of A3, because that's just one matrix, there is no computation involved in that. And then the cost of multiplying these two together is basically you have a 10 by 5 matrix and then a 5 by 50. So that's 10 by 5 times 50, and so you have these two. So the total cost comes out to be the cost of the first matrix, the cost of second matrix, times the cost of multiplying it together. So that's a total of 7,500 scalar multiplications. That's option 1, okay? Option 2 is similarly done, but since you have much larger matrices coming in, so the final result is much larger, in fact, 10 times larger, okay? Simply because the A2, A3 matrix is much larger because you actually have the number of rows in A2 now still present, okay? So clearly, the order in which you put the parentheses in a matrix chain multiplication makes a big difference, okay, in terms of the number of scalar multiplications that you have to perform. So it's important to be able to, if you, especially as I gave you some examples in the last lecture, that there are a lot of applications for this, especially in, for example, game theory or networks where you have to multiply a very large number of matrices. And so you need to be able to figure out if you have all of these matrices together, then what's the best way to put the parentheses in, okay? So now let's take a look and see if you want to do an exhaustive solution, how difficult would that be? Okay, so that's always our first attempt. Let's see if we can just break down the problem and just do it in brute force manner. Okay, and if you can do it in the brute force manner, which is not very complex, then that's great. All right, but let's see how far we get. So I'm going to define Pn, which is the number of possible parenthesizations with n matrices. Okay, the number of possible parenthesizations with n matrices. So P1, okay, which is basically one matrix. So obviously there is no parenthesizations. If you have two matrices, then clearly there is no parenthesizations either, because there's only one way to multiply A1 and A2. Okay, so P2 is also one, P1 is also one, which is the number of parenthesizations. P3, however, is 2. Okay, why? Because we just saw that example. You could either put the parentheses over here, or you could put the parentheses over here. Two possible ways. And if you think about it, then this corresponds to P2, and this corresponds to P1. Okay, so essentially P3 can be thought of as a product of P1 times P2 plus P2 times P1. Okay, so this comes out to be 1 times 1 plus 1 times 1, which comes out to be two possible ways. That doesn't seem to be growing very fast. It seems to be rather slow growing, polynomial perhaps. But let's take a look at P4, and you fairly quickly realize that this is going to become larger and larger pretty fast. All right. So P4 is now going to have possibly 5 different ways of putting the parentheses. Okay. So the first one is P1 times P3. So in other words, you've separated P1 and you're now saying times P3. Okay. But P3, we already know there are 2 ways to handle this. All right. So the yellow stuff is the number of ways that you can actually do P3, which is already 2. Then you can do P2 times P2. There's only one way to do this. Okay, you put you do two matrices, and then you multiply them together. Or you can do P3 times P1, and P3 again. We already know that there are 2 ways to solve that. 2 ways to put the parentheses in, and so this comes out to be 2. So P4 is in fact P1 times P3, 1 times 2, plus 1 times 1, plus 2 times 1. It comes out to be 5 possible ways of putting in the parentheses. Okay, so can somebody give me an equation for the general recursive equation? So what would Pn be? What seems to be Pn? Yes. Yeah, that makes sense. Right? 1 to n, yeah. Well, n minus 1, right? Yeah. So you can see that there it doesn't go all the way up to P4. So the question now is, what is the complexity of this? Has anybody seen an equation like this before? And how would you determine the complexity of this? So it may not be completely obvious, but it can be figured out. So here's the equation. For n is equal to 1, that's 1. And for n greater than or equal to 2, this is the equation, which is what Yuvraj just told us. And the complexity is not completely obvious, but you can figure this out. And you can show that it's actually omega, a lower bound of exponent. Okay, so 2 to the power n. So the actual equation is a little complex, but basically it is an exponentially growing function. And so if it's exponentially growing, then obviously an exhaustive solution doesn't seem to be very appealing, right? So we're going to either do a greedy solution or we're going to do a dynamic programming solution, right? But since we're already on the topic of dynamic programming, we know that it's going to be a DP solution. And so for DP, what are the usual checks? How do we make sure that it is a legit DP problem? What are the few checks that we need to perform on this problem? We've done this frequently enough, so you should now have this right at the tip of your tongue. Yes? Yeah, so first we need to do an optimal substructure. And after that, so what are the sequence of steps? Optimal substructure, and the next step would be? Yes? So overlapping subproblems. But before you get overlapping subproblems, there's an intermediate step before you actually get to the overlapping subproblems. There is an intermediate step, which is, so you showed the optimal substructure. The optimal substructure leads us to what? Leads us to a recursive solution. Okay, so hopefully this is coming back to you, right? So the optimal substructure says that we can have a recursive solution. That comes in directly from the fact that it's an optimal substructure. Now, once you have the recursive solution, now it's still not clear whether you can have a DP solution to this, okay? And so we saw this several times in all the problems, rod cutting and so on, the LCS, that we have a recursive solution, but the recursive solution could be kind of tricky depending on whether you are doing a top-down solution or a bottom-up solution. And then if you can find that there are overlapping substructures to the recursive solution, then you can start thinking about a DP solution. Okay, and then you have to figure out whether you're going to go bottom up or top down. Okay, and generally it's a bottom up solution simply because you can sort of, as you're going up, you can save the solutions into tables and then use the previous solutions to come up with better solutions. Okay, or as you go upwards, we can use the tables below to get to the next level, to the next layer. All right, so those are the sequence of steps that we've repeatedly done in the last few examples of dynamic programming problems. So let's see if we can do the same thing over here. So here's a tree representation of the same problem. It becomes a little easier to take a look at the problem and have intuition about it. And you can see that we can sort of show A1 times A2 multiplied by A3 times A4 as a tree, which is initially multiplying A1 times A2, all right? And then you're multiplying it by A3, and then you're multiplying by A4, right? So the parentheses can be converted into different trees. And you can see that each one of these trees is somewhat unique. And so this was an example with n is equal to 4, where you had 5 different possible parenthesizations or tree representations. So first question, do we have an optimal substructure? Yes, so if you're trying to multiply A1 through AI through AJ, from AI through AJ, which is sort of a subproblem of A1 through AN. Now the question is, does it have an optimal substructure? Yes. So let me see if I followed what you just said. So if you can find a parenthesization that you just said, So let's assume that you're breaking the parentheses around some number m. Okay, so you're doing AI through AM first, and then you're doing AM plus 1 through AJ. Okay, and could you continue with your, I didn't quite follow after that. So initially you find, Okay, that's a good suggestion. However, you're not addressing my question. My question is, does it have optimal substructure? Okay, you're trying to get to a solution, and we've quite a ways from the actual solution. Okay, because we're going to apply dynamic programming, and your solution might be great, right? I'm not criticizing that. All I'm saying is that let's see if dynamic programming is applicable to this problem. Okay, and so we're going to go through that series of questions. First thing is, does it have optimal substructure? Because what you're trying to do is trying to jump at a solution, and you can get, it can become really complicated. Okay, if you try to directly find a solution, which may be good if you can, if it was a greedy problem. Okay, in greedy problems, generally you have simple solutions. You look at the local optimum, and the local optima is generally gives you the global optimum as well. Okay, but in problems which need to be addressed by DP, you don't have that nice property. Okay, and you're not going to find a locally optimal solution which is going to be globally optimal. Okay, so we're going to tackle it in a methodical manner. We're going to say, well, can we first of all see whether a DP solution is applicable? And for that, we're going to check whether it's got optimal substructure, a recursive solution. Does the recursive solution have overlapping subproblems? And then whether we need to go bottom up or top down, and how do we actually save the intermediate data? So that's the whole series of steps that we need to follow for every DP problem. Okay, but rest your thought might come in handy later on. Okay, so let's think about whether it has an optimal substructure. And we know that the optimal substructure, and I'm saying this repeatedly in every DP lecture, I say, how do you actually start to prove whether there's optimal substructure? And I asked this question in the last lecture, and eventually got some of you guys to answer that. So how do you start to prove an optimal substructure? And now you guys should be getting a hang of this, right? How do we prove an optimal substructure? You've done this at least 4 times before, starting with the minimum spanning tree, then the shortest path, then rod cutting, then LCS. It's 4 problems, right? So you just need to think about it again. Yes. Sorry, say that again. Well, yeah, you jumping at the solution, okay? You're jumping at the proof. But before we get to the proof, Kyle. Yeah, that's one way that you basically show that if you take a smaller problem and if you can modify it, does it make the problem worse or not? Okay, but there's a slightly different way of thinking about it, maybe a top-down approach to think about this. So I'm going to say it one more time, and the next problem you guys are going to tell me, okay? So we're going to start by assuming an optimal solution, okay? Start by assuming an optimal solution, right? And then, and we've done this repeatedly, take a solution, assume it is optimal, okay? take a smaller problem, assume that it is, and we try to prove that that smaller subproblem is also optimal. And then we apply the cut and paste to prove the contrary. Okay, so now can somebody tell me how would you go about doing the optimal substructure statement and then the proof for this problem? So I've sort of given you the big picture, right? You assume that there is an optimal solution, and then you say, well, so go ahead, give it a shot. I have sort of given you a hint over here. So you've got, let's say, AI through AJ. So you're going to assume that this is already optimal, that the parentheses is already optimal for AI through AJ. And by that, let's assume that it comprises of a parentheses somewhere around AM and AM plus 1. Okay. So what we're basically saying is that these two are what? These two are individually. That if this whole thing is optimal, if the whole expression has an optimal, it has been divided up optimally, then any two parts are also optimal, right? Now, this is where now the cut and paste problem proof comes in. How do we prove the contrary? Okay. Now we're going to say, well, let's assume that this and this are also individually optimal. Okay. And now let's take a look at this and let's apply the cut and paste proof. So how would you apply the cut and paste proof over here? Yes, Lola. Yeah. Yeah, very good. So basically what Logan is saying is that you assume that if this were not optimal, okay, and the parentheses inside this were not done in the optimum way, okay, let's make proof by contradiction by doing the cut and paste proof. And we say, well, let's assume that you have some other parenthesization, okay, and we call this by prime, okay, and you can call this S1, this is, let's say, S2, this is set S1, S2, and now we have, this is S1 prime, okay? And now what we're basically saying is that S1 prime, okay, the substructure S1 prime is better than S1, okay? So if it is, in fact, has better parenthesization than S1, then we're going to replace, and let's say this is the overall parenthesization is S, and so we're going to form another solution, which is S prime, which comprises of S1 prime and S2, okay? We're going to have S1 prime, which has now replaced S1. And now we're saying that S1 prime has a lower cost. Okay, so if S1 prime has a lower cost, then can you say that the overall solution would have, if S1 prime has a lower cost, then the overall solution S prime is going to have a lower cost as compared to S. Yeah. So basically, this is what we've just said, is that let's assume that you have some optimal split. I've used a different variable over here, K, okay? So just repeating what I just said, and then we're going to assume that we're going to basically say that these individually must each be optimal, okay? And the proof is that the standard cut and paste, we're basically saying proof by contradiction. We're saying that if AI through AK is not optimal, okay, then let's assume that you have a better solution, which is AI through AK A prime, all right? And we're going to form an S prime. So this is S, and this is S prime. And S prime has now replaced this portion over here, okay, this portion over here with the one which has the prime, which is supposedly more optimal, which means that it has a lower cost, okay? And so now what we're saying is that if that is the case, then S prime will have a lower cost than S, okay? So the cost of S prime is now going to be less than the cost of S, okay? And that's a contradiction. So are we pretty much done, or is there some detail that we perhaps still need to look at? We're essentially saying the cost of S prime is going to be less than the cost of S. But the cost of each one of these is a little tricky, isn't it? So we need to make sure that we're not glossing over some details, and we need to go back and make sure that this is in fact true, okay? And for that, let's just review what I said earlier was, if you look at the way that we done the multiplication, we said that if you're doing two multiplications, then it's basically the cost of the first matrix plus the cost of the second matrix plus the cost of multiplying it together, okay? So coming back over here, what exactly do we still need to make sure that we're not glossing over some details which perhaps might come back and bite us? Okay, so if the cost of this, so in other words, the cost is basically the cost of S1, okay, the cost of S1 plus the cost of, this is the cost of S, is the cost of S1 plus the cost of S2 plus the cost of multiplying S1 and S2, all right? That would be the cost of this substructure. And so we're saying that this particular cost is going to be smaller than the cost of S1. Cost of S2 is going to remain the same, right? What about this guy? Is this going to be the same? If we replace S1 by S, so this is now going to be replaced by cost of S1 prime and S2. Is this also going to remain the same? Two people shaking their heads. And one of you guys tell me why it's not going to be the same. Yeah. Think again. What is the cost of this actually equal to in terms of scalar multiplications? Remember, the cost of the scalar multiplications only depends on what? Because we're not looking at the actual numbers inside. We're looking at the size of the matrices. So the size of the matrices change. Is S1 and S1 prime of the same size? Would S1 and S1 prime be of the same size? Yeah. Okay, you're right. Yeah, it's giving you the same. It's giving you the same final result. It's just that it's the parenthesization is different. And if you think about it in another way, is that if S1 prime is being multiplied by S2, the number of columns of S1 prime has to be equal to that of S2. And the first matrix of S1 prime has the same number of rows. So the size of S1 prime is still the same as the size of S1. Okay. And if that is the case, then the cost of S1 times S2, it has to be equal to the cost of S1 prime times S2. Okay. So essentially, this doesn't change, and only this has become smaller. And so now we can make the statement that in fact, cost of S prime is going to be less than cost of S, which is now a proof of contradiction. Okay, so sometimes you just have to make sure that the cut and paste argument is not, very simplistically applied, and you make a statement when you haven't really done all the detailed calculations. Okay. So this is basically what I just said, that the cost of S1, S2 is the cost of S1 plus the cost of S2 times the cost of multiplying this together. And hopefully you followed the earlier logic to see why this would be a proof by contradiction, to show that this in fact does have an optimal substructure. Okay, so first issue down, we've solved the first problem, which is to figure out that it does have an optimal substructure. All right. Now let's take a look at the next problem, which is, does it have overlapping subproblems? Okay. So I'm showing you the matrix, the tree representations, and that can perhaps give us some idea that does it have overlapping subproblems. Okay. So can anybody see the overlapping subproblems here? Yes. Yeah. Cost of S1 changes, but not the cost of S1 times S2. Okay. So S1 internally comprises of two sub matrices. Okay. Now their sizes have changed, but the size of S1 prime and S1 have not changed. The overall size hasn't changed. Think about going back to this particular problem. Okay, think about this. So by doing different parenthesizations, we basically said that the individual cost, the individual size of the subproblems has changed. Okay, but the overall size of A1, A2, A3 will not change, regardless of how you do the parenthesizations. After you've multiplied this whole series of matrices, A1 times A2 times A3, then that whole matrix is going to remain the same size. Okay. But when you're doing the actual costing, that will depend on how you doing the parenthesizations. Okay, so coming back over here, basically what we're saying is that the cost of S1 and S1 prime are different because we're assuming that the internal parenthesization of S1 and S1 prime are done differently. Okay, and that is our initial assumption, that there is some other optimal substructure which is in fact has a lower cost. Okay, that is a proof by contradiction. And however, the cost of S1 times S2 doesn't change because now we're looking at the bigger picture. We're looking at S1 after it's been calculated. And the size of S1 is going to be the same as size of S1 prime. Okay. So now going forward, can anybody see the overlapping subproblems? So we have 5 different ways of doing it, of doing these multiplications. And Hopefully it's not too hard to see the overlapping subproblems. Just have to stare at it. Overlapping subproblems. Yes. So A1 times A2 is happening twice. What others? And what else? A3 times A4 is happening twice. A2 times A3 is also happening twice. So you can see that there is, even in this simple problem, there are a whole bunch of overlapping subproblems. Okay. And I've shown that over here in color, so you can see that there are certainly overlapping subproblems. Okay. So great. We've gotten the two major problems resolved, two major questions. And so now we can proceed with a dynamic programming solution. Okay. Now, we generally also have to address the issue as to how are we actually going to save, how are we going to do the memoization? Okay. So do we do the memoization by going bottom up? Clearly, top down, if you recall, wasn't generally a good solution. Okay, that basically said that we start with recursion, we do a top down, and every time we saw a solution, well, we would try to save it. And next time when we look at a problem, we would say, well, has this been saved earlier or not? So, and that also had to require a lot of recursion memory stack building up. Okay, and the other way was going bottom up, right? So in bottom up, we basically said, well, we know that the bigger problems require solutions to smaller problems. So let's just go bottom up, okay? And the rod cutting was the classic example. We started off by saying, let's look at a rod of size 1, then rod of size 2, and then 3 and 4, and so on. And basically said, well, we will save the solutions to rod of size 2 or rod of size 3. And then when we looking at rod of size 4, then we're going to say, well, it's going to need a rod of size 3 and maybe some combination of 3 and 2, and we'll have saved those already. Okay, so we'll have memorized them. So generally, a bottom-up solution makes more sense. Okay, starting with small problems and then going to bigger problems. So any thought of how we could actually convert this into a DP algorithm, which is sort of going in a bottom-up manner? So where would you start off? Yes. Okay, so just go a little slow. So you're saying that let's figure out what's the number of multiplications for A1, A2, and what else? Yeah. Okay, so we take the smallest one from there, and then we need to still figure out. Let's say we're trying to solve the problem A1, A2, A3. Okay, forget about A4 for a few minutes. So let's say we're trying to solve the problem A1, A2, and A3. This is something we've already seen before, and we know that there are two possible solutions to it. One is A1, A2, okay? And the other one was, where is the other one? Which is basically saying, here's the other one, which is A1. We do A2, A3 first, and then multiply by A1, versus doing A1, A2 first, and then multiply by A3, right? So, so can you sort of restate your case? So let's forget about A4 for the timing. Let's just look at A1, A2, and A2 and A3. Now, can you restate your suggestion? So remember, in dynamic programming, we essentially saying we don't know the solution to the general case. Okay, it's not like the greedy case where you say the locally optimal solution is going to be globally optimum. In dynamic programming, we're going to explore all possible solutions, right? But not in a simplistic brute force manner, in a simplistic exhaustive manner. We're going to be a little intelligent about it. We're going to solve small problems first, save those results, and then look at bigger problems. And then because we've saved the solutions to the smaller problems, we don't have to repeat the solutions again because we know that there are overlapping subproblems. And so we're going to build up the solution and eventually come up with a solution which is not as complex as the exhaustive solution, the brute force method, okay? So you're sort of on the right track. Now, just think about it once again. You said that let's compute A1, A2, okay? Let's compute A2 times A3. So that's perfectly fine. So let's say we've done that. Is that enough for us to be able to make a decision between which one of these is actually better? So is this going to be better? Or is this going to be better? Just looking at the subproblem of A1, A2, A3. And how do we actually know which one is going to be better? And remember, dynamic programming doesn't really say you have a magic wand, right? It simply says you have to compute all the complexities of the two problems and just save the result. That's all it's saying, memoization, okay? So how do we actually figure out which one is better? Let's say this is option 1 and this is option 2. No magic wand, okay? How do you do it? Is the obvious, you just compute it, right? You just compute both of these cases, and then what do? So you've got two solutions, and now remember what do we do? In memoization, we say, well, we're going to keep track of the worst solution? No, the better solution, right? So if you cut up the rod in different ways, and you know that the best revenue that you can generate if you take a size of size 8 is by dividing up into size 4 or 6 and 2, then you simply have to keep track of that. Okay, but you still have to do the hard work. You actually have to do the computation. So there's no simple solution. You just have to look at all the alternatives. All right, so here are the two alternatives. There's option 1 and option 2. You compute both of them, and then you compare them, and you say which one is better. And then you say, well, because I've computed both of them, I now know which one is better. I'm just going to save that perhaps in a separate table. So remember, you have two tables going on, generally speaking. The actual computations and the route to get to that. You remember we did this in the LCS as well. We saved the route. Yeah. The cost. Yeah. So you're not computing the actual multiplications. We don't. You can assume in all of this that you actually have blank matrices. Okay. The actual numbers inside the matrices are completely irrelevant. There could be any real numbers and so on, right? So all we're doing is we're computing the cost of multiplying, which is basically given by the dimensions. So remember when I said the way the problem is being given to you is that you have the number n, and then you have the size of the dimensions of each one of these matrices. You don't actually have the actual matrices because the actual content of the matrices is not relevant. Okay, all you need to know is what are the dimensions of the matrices and how many matrices do you have. Okay, so essentially, how would we compute this? We've already done this before. Okay, so we did A1 times A2, which is basically P0 times P1 times P2, and then we did the computations. Remember, we did this whole example, and then we did the second option, right? So we know that we can calculate this based on the dimensions given. P0, P1, P2, and P3. Based on that, we can evaluate what is the cost of option 1 versus the cost of option 2. We compare those, and for the example that I had given earlier, we saw that the first option was better. Okay, so if the first option was better, we need to keep track of that. Okay, and we need to keep track of that by saying, well, where did we separate the two matrices? Okay, so what we're going to say is we're going to keep track of this number over here. Okay, the point which separated AM and AM plus 1. Okay, the point where we bifurcated the two. Okay, whether we did it at 2 and 3 or 1 and 2. Okay, so if it was this case was better, then we would keep track of the number 1 over here. If this case was better, then we'd keep track of the number 2. Okay, and we'd keep track of this in a separate table, which is basically memorization, which is remembering which order give us the more economical solution, or the lower cost solution. So basically, this is what dynamic programming is doing, is that it's going to evaluate the different options, is going to figure out which is better, and it's going to save it. Okay. To do that, you've got an algorithm which doesn't look very simple. Okay. So here's how we're going to do it. We're going to define the following. We're going to define AI colon J, okay, as the product, the intermediate product, AI through AJ, okay. We're going to define the minimum number of scalar multiplications. So this is an optimal solution between I to calculate from AI through AJ, okay. So MIJ is the minimum number of scalar multiplications to get to multiply AI through AJ, okay. And then we're going to say, well, let's assume that if we did a split at AK and AK plus 1, okay, so we're splitting it up over here between AK and AK plus 1, all right. It's going from I to J, and we're splitting it up in the middle somewhere between K and K plus 1, okay. And so the dimensions of these will be given by what? This is AI. So remember, the number of rows is going to be I minus 1. Okay. Going back to the first matrix, which was A1, the dimensions of P0 times P1. Okay. So the dimensions of this is going to be Pi minus 1 times Pk. Okay. Pi minus 1 times Pk. And the dimensions of this are going to be Pk plus 1 minus 1, which is Pk times Pj. Okay. Is that clear? That the dimensions of these two substructures are going to be given by the first and the last matrix. Right? So the cost of multiplying these two is simply going to depend on Pi minus 1, the number of rows in the first matrix, nothing else over here. Pk, the number of columns or rows in the intermediate matrix, and the last matrix, Pj. Okay, so basically what we said is that if we have subcategorization between AK and AK plus 1, then we can figure out what the cost is to multiply these two substructures. Okay, and that simply depends on the size of each one of those submatrices. And the size of this is Pi minus 1 times Pk. The size of this is going to be Pk times Pj. And so the cost of multiplying these two is going to be Pi minus 1 times Pk times Pj. Okay. So the cost, the minimum cost, the overall minimum cost is then going to be, can be written down recursively as the cost of multiplying these two matrices plus the individual cost of calculating the cost of each one of these substructures, which is exactly what I did earlier, right? Remember that we had this equation CS1 plus cost of CS2 plus the cost of multiplying CS1, S1 times S2. Okay, so this is the cost of multiplying these two. This is the cost of CS1, and this is the cost of CS2. Okay. So now we can say that we can write a recursive solution. Okay. And can somebody tell me what the recursive solution would be? So this is assuming that we've done a split at K. Now in dynamic programming, you're going to evaluate all the possible solutions and figure out which is the minimum cost. Then you're going to memorize it. Okay. So how do you figure out what is the minimum cost for Mij? This was assuming that the split is done at some arbitrary value K. Right? Now, how do you find out the optimal value of M, which is the cost of multiplying all the way from I to J? So we've broken it down into saying that the overall cost from I to J is basically can be written down as the cost of, if you had split it up into two subparts, you can call this S1 and S2. Okay, at some arbitrary value, some arbitrary splitting point K and K plus 1. But now we need to find the optimal solution. So what's the optimal solution going to be? We just did this, right? We said that you've got two possible ways, and you do the multiplication, and you pick the minimum of the two, right? Because you want the minimum cost. And in this case, we picked two possible ways of splitting it up. For K is equal to 2 over here. So K is equal to this one. So we had different splits. Okay, we split it up at K is equal to 2 over here, and we split this one at K is equal to 1. Okay. So how did you do it? We calculated the two options, and then we took the minimum of the two, right? So in this case, how should we do it? How would you rewrite this into an optimal solution? Mij, and we've set some arbitrary value of K, and now we have to look through all the possible values of K, right? And what would be the values of K? What would be the range of K? Now this is going from AI through AJ. So what could be possible values of splitting it up? K would go from where to where? And remember, the split is at AK and AK plus 1. Okay, so if the split was right here, this would be K is equal to I, right? If the split was over here, this would be K is equal to I plus 1. The last split would be at AJ minus 1. So in other words, the range of K is going from I to J minus 1, right? And so we're going to vary K from I to J minus 1. We're going to calculate the total cost of each one of these and then pick the minimum one. And then obviously we've got to memorize, which means that we have to remember which value of K was actually used. Okay. So here is the solution. We're going from K is equal to I to J minus 1 to less than J. if I is equal to j, then obviously you've just got one matrix, and the number so the minimum number of multiplications would be 0 because you don't have to multiply. But if I is less than j, then we're going to do this series of calculations. We're going to repeat this for all values of all possible splits. Okay, and once we've done all the possible calculations, we tabulate all of them and say which one is the smallest. Okay, and we're going to memorize that particular value of k, which was the optimal solution for that particular problem. Okay, so now we need to be able to have a tabular solution that can actually work. Okay, so I think we did this, as we saw in rod cutting solution, it was one dimension. In LCS, we had a two-dimensional solution, and we're sort of going through that. And gradually, as you can see, things are becoming a little bit more complex. Okay, so this is going to be a little bit more complex in LCS, where you're simply comparing characters, and you're remembering whether you need to go up or left, right? You remember the direction, and you're keeping track of a few things like that. In this case, it's going to be a little bit more tricky. So that DP problems can become somewhat hairy, okay? And the number of calculations can become quite large. However, as long as you implementing this in some kind of a automated program, the problem, as long as you're making sure that the boundary conditions are right, that one set of equations is implemented correctly, the rest of it is simply repetition, okay? And while if you're doing it manually, it can become pretty hairy, but otherwise, but what is important is that you understand the logic behind it, okay? So let's try to see how this particular algorithm actually works. So this is called matrix chain order, right? It's going to start off by taking two matrices. The first matrix is going to be called M matrix, and the other one is called S matrix. Okay, so M, this is the M matrix or table. So the M table is where we're actually going to store the calculations of how many multiplications did it take to calculate the smaller matrices. Okay, and S is simply going to be the memoization, the split, okay, which particular value of k was chosen. So let's start. Initially, what we're doing is we're simply going to do some initialization. For I is equal to 1 to n, we're going to, and now this table this is how it's been done in the book. I don't really like it, but that's how CLRS has done it. It's sort of split, it's sort of turned a two-dimensional table, which could have been nicely represented as I and J in this manner, and looking at, let's say, the top right triangle of this. But what they've done is they've sort of rotated this, okay? And they've rotated this way. So in other words, you have J going this way and I, all right? So I is basically going from 1 to n, and n is equal to 6. J is also going from 1 to 6. Okay, so this is a two-dimensional table which we're going to figure out how to do the calculations. But we're not going to go through all the entries. We just do a few entries so that we understand, what's the structure of this calculation. So initially, it's basically going to say that each one of these is going to represent. Remember, the M table is what? The M table is basically saying that Mij is the minimum number of scalar multiplications to compute the matrix AI through J. Okay. So where do you think the solution will be? What are we looking for at the end? I'm going to. So what are we basically looking for in terms of the solution? For if you have A1 through AN, right, then what would tell us what is the total number of multiplications based on just this equation? Okay, just based on this definition, Mij is the scalar multiplications going from Ai through Aj, then clearly we're looking for a solution which is M going from what, where to where? We want the solution from 1 through n, right? So we're looking for the value M1 through n. Okay, basically it says that M1 comma n would be finally give us the result, which is the number of scalar multiplications to multiply A1 through AN. Okay, so this is what we're looking for, M1 comma n. So let's take a look. Where does M1 comma n show up? So hopefully you can see that M1 comma n corresponds to this particular entry in this two-dimensional table. Okay, I comma j. I is 1 over here, and j is 6. Okay, so this here is supposed to be the apex of this particular table, and that is hopefully where we're going to sort of do our calculations and head upwards. Okay, and that may be the reason why it's sort of shown in a tilted way. Okay, so now the first thing we're doing is we're saying that mi comma I is all set to 0. Now, why does that make sense? What does mi comma I represent? I comma I. Go back over here. Why should mi comma I be 0? Yes. Yeah. So mi comma I simply represents the matrix AI. Okay, and it's just a single matrix. So the number of multiplications is clearly 0. Okay, because that itself doesn't need to be multiplied by anything. So mi comma I is going to be 0. So where does that correspond to? So 1 comma 1 is going to be 0. 2 comma 2 is going to be 0. And so you can see that the first level is going to be all zeros. Okay, so this is sort of the level. And now we're going to take L and go upwards. So we've done the level 0, okay? And now we're going to go for level 1, level 2, and all the way. We're sort of going to go bottom upwards, okay? But in a slightly not so obvious manner. So now we're going to compute for I is equal to 1. Now, whenever you have these nested loops, it's always a good idea to instead of trying to do it in a rough kind of manner, it's better to actually draw a matrix or table and to keep track of the numbers. So basically what we're saying is that L, these are the variables, L, and then I, and then J, and then K, a whole bunch of them, okay? So now some of these are simply constants depending on the earlier values. So J is simply based on I and L, okay? But the actual number of loops is L, I, and K. So it's a triply nested equation, okay? Triple nested. So these are the values which are going to be changing, L, I, and K.